Hello, everybody. Thank you for joining us and welcome to the Astro 3D ECL Astronomers in Australia seminar series. My name is Yifei Jin. I'm a PhD student at the Australian National University. Before we begin, it's important for us to acknowledge the traditional custodians of the land on which we meet today. The Aboriginal and Torres Strait Islander people were Australia's first astronomers that will acknowledge their long-standing systems of knowledge on which we continue to build. We acknowledge the traditional custodians of the unceded lands on which we are meeting today. I am speaking with you today from the land of Ngunnawal and Ngambri country. Our first speaker, Bronwyn Reichardt Chu, is speaking to you from Wurundjeri people of Kulin Nation. And our second speaker, Junior Santusi, is speaking from the land of Badigo people. We pay our respects to their elders past and present and extend that respect to all First people joining us here today. So why are we here? This series is facilitated by Astro 3D, the ARC Center of Excellence for All-Sky Astrophysics in 3 dimensions. COVID-19 has affected our ability to travel and present at international seminars this year, especially for us in Australia. The time zones mean that often meetings take place at 2 or 3 in the morning. This lack of opportunity to network could disadvantage junior astronomers when entering the job market. This series aims to combat these issues by providing a platform for junior Australian astronomers to present their work to the world. There will be 2 talks over the hour. Each will be 20 minutes in length, with 5 minutes for questions at the end of each talk. Please save your questions until the end of each talk. Feel free to use the chat function to ask your question if you prefer, and I can read it out for you. These talks are being recorded and will be placed afterwards on the Astro 3D YouTube channel for educational and scientific purpose. By being here today, we are agreeing to abide by Astro 3D's meeting code of conduct. I've already warned the speakers of this, but because of the limitations of Zoom, I will need to interrupt with 5 minutes to go in each talk. So first, our first speaker is Bron Reichardt Chu, who is a PhD student from Swinburne University of Technology. So Bron, the screen is yours.
Hi everyone, I'm Bron Reichardt Chu. I'm a PhD student at Swinburne, and I'm going to be talking to you about some things that we've been doing with the DUVET survey. So we're extremely interested in gas-rich turbulent disk galaxies, and we're particularly interested in outflows because they may be intricately linked to star formation processes. So star formation processes, I thought I might just go back to basics for a moment so that we are all starting on the same page. So star formation occurs when a cold molecular gas cloud collapses under the force of gravity. If we assume that the cloud collapses in freefall, then we would expect a cloud to collapse on a freefall timescale of 1 to 10 million years, depending on the density of the cloud. However, in observations of both spatially resolved galaxies and entire galaxies, we find gas depletion times of around 2 gigayears, which is much longer than we expect. So there must be another force which is acting against gravity. So as the molecular cloud collapses to form stars, young massive stars and supernovae give energy and momentum to the surrounding gas. This causes turbulence, acting against the gravitational pressure and causing the longer timescales that we observe. This process is known as stellar feedback. Simulations can't reproduce basic properties of galaxies like the galaxy mass function, typical galaxy sizes, and the Kenneckett-Schmidt law when stellar feedback is not included. But simulations usually rely on using feedback prescriptions, which are tuned to reproduce empirical galaxy parameter scaling relations. So this means that we really need to understand feedback observationally so that we can inform those scaling relations. And so we need to have observational constraints on stellar feedback. Outflows are an observational signature of this feedback process. For example, if a supernova explodes and pushes gas outwards, some of that gas will leave the plane of the galaxy, possibly to escape the galaxy altogether and enrich the surrounding CGM, or to fall back onto the galaxy in a galactic fountain and be recycled in the next generation of stars. And some of that gas will expand within the plane of the galaxy itself, introducing turbulence into the surrounding gas cloud and affecting star formation processes within the galaxy. So by observing the outflows which break out of the galaxy disk, we can better understand the feedback effects which occur within the disk of the galaxy itself. As well as being an observational tracer of star formation feedback, outflows are an integral part of the baryon cycle. However, we don't fully understand star formation feedback processes yet. So this is a plot from Fisher et al. 2019. On the x-axis, we have the pressure. So this is the gravitational pressure, which is acting on the disk of the galaxy. And on the y-axis, we have the star formation rate surface density. So what we expect is that as more pressure on the gas in the disk, the more star formation there will be occurring. This doesn't lead to runaway star formation because of the star formation feedback, which regulates star formation, and it's included in this eta value here. So currently, widely used models only include feedback driven by supernovae, and that gives us this dashed theoretical prediction here. The points on this plot represent galaxies at a range of redshifts. However, and we can see that they all do follow that general trend, which we were expecting, as they measure a greater pressure on the disk of the galaxy. They also measure a higher star formation rate surface density. But the theory is failing by an order of magnitude in these high star formation rate surface density galaxies. So there's something missing from these feedback assumptions. This could be an extra component for feedback, which hasn't been included in the model. It's particularly important to study these high star formation rate surface density galaxies because they are the types of galaxies which are typically present at redshifts 1 to 2, when the majority of stars in our universe were formed. So if we don't understand the feedback processes which are regulating star formation in high star formation rate surface density galaxies, we don't actually understand how the majority of stars in our universe were formed. But it's very difficult to study feedback in these galaxies, since emission from outflows is very faint compared to the galaxy itself. This is where DUVET comes in. So DUVET is a survey of starbursting galaxies in our nearby universe. This is a plot of star formation rate against stellar mass. In grey, we have SDSS sample galaxies with the dashed line showing the main sequence for those galaxies. The blue points are the DUVET galaxies. So DUVET galaxies are chosen to be starbursting. They have star formation rates 5 to 15 times that main sequence value. They're also chosen to be compact so that they reach that high star formation rate surface densities that we really want to be exploring. They're also chosen to be disk galaxies with well-ordered rotation fields and exponentially decreasing profiles so that there's no crazy kinematics going on. There are 27 galaxies in the DUVET sample, which have been observed using KCWI. Because they're compact and in our local universe, this means that they fit nicely into the field of view of KCWI, which means that we have spatially resolved data for all of our galaxies on scales of a few hundred parsecs. We also have data from ALMA and GMOS, and many of our targets have been chosen to overlap with HST COS observations. So it will be possible to compare outflow measurements in different phases of gas. So today I want to talk to you in particular about two DUVET projects, measuring outflow metallicities in an edge-on galaxy and mapping outflow kinematics in a face-on galaxy. These projects have become possible because of IFU instruments like KCWI, MUSE, and hopefully soon JWST. So firstly, measuring outflow metallicities in an edge-on galaxy. Metallicities are commonly measured in galaxies using the strong-line method. This assumes a model with a particular relationship between the ionization, the electron density, the pressure, and the metallicity. This is quite useful in the disks of galaxies, where we understand how these parameters interact and change. However, when we move off the plane of a galaxy, Gas far from the inner disk has varying ionization conditions, and the degeneracies between these parameters make it difficult to pin down a metallicity for gas which is away from the galaxy. The direct method uses auroral lines like 034363, which depend directly on the electron temperature. And the electron temperature depends in turn directly on the metallicity. And so we'd think that this might be a better method to use when trying to map metallicities away from galaxy disks. However, auroral lines are typically 50 to 100 times fainter than strong lines. And when you're trying to map gas, which is away from a galaxy disk, it's really super faint anyway. And so this is extremely observationally challenging. But we have managed to do this for one of our galaxies from the DUVET sample. So this is work which has been done by Alex Cameron, who just finished his PhD at Melbourne Uni and has moved to do a postdoc at Oxford. This is Markarian 1486. It's a disk-like edge-on galaxy from the DUVET sample. This grayscale image shows the U-band flux. In orange, we see contours which show the extended H-alpha emission, and the magenta footprint is the region in which we can observe 4363 with the signal to noise greater than 5. This means that we can start to map metallicities of the gas which is off the plane of the disk. So here Alex has plotted on the y-axis the 4363 to 5007 line ratio, which gives us the electron temperature. On the x-axis is the 032 line ratio, which corresponds to the ionization parameter. Each line across this plot corresponds to constant metallicity, and these come from photoionization modeling. Each point is from the DUVET observations. For the minor and the major axes of Markarian 1486, and they're colored by their distance off the disk. And so if we concentrate on the top panel for a moment, these are the minor axis profile points. In yellow, we have points which are on the plane of the galaxy, and in blue and red, we have points which are to the southeast and northwest of the galaxy plane, respectively. And the thing to note here is that the points with the highest metallicity are those points which are off the plane of the disk. If we look at the major axis profile, black points are those points which are along the axis of the galaxy. The orange and green points are those which are beyond the 90% radius on the major axis. And the thing to note in this panel is that the points with the lowest metallicity are those which are beyond the 90% radius on the major axis. So we're finding that the highest metallicity is above the plane of the galaxy and the lowest metallicity is outside the 90% radius on the major axis. We can use these electron temperatures and convert them to their corresponding metallicities and map them. And so here we have the map. Again, we can see that the highest metallicities are off the plane of the galaxy and the lowest metallicities are beyond that 90% radius on the major axis. And so this is consistent with what we might expect from the baryon cycle. So what we think we may be observing is a very metal poor inflow, accreting gas onto the disk of the galaxy and driving a starburst, which is then driving in turn a metal-enriched outflow. And this is what we expect from the baryon cycle. So the second project I'd like to talk about is measuring outflow kinematics in a face-on galaxy. So we know from observations in our local universe that young massive stars and supernovae disrupt their local environments, and they're major drivers of star formation feedback. But we don't quite understand which one is dominant and in which environments are they dominant. So what we would like to know is, does energy or momentum primarily drive star formation outflows? In energy models, supernovae explode and give energy to the surrounding gas, driving an outflow which has a velocity which is proportional to the star formation rate to the 0.1. In momentum-driven models, young massive stars radiate huge amounts of photons, high energy photons, and these couple to the surrounding gas and dust, giving them the momentum and driving an outflow which has a velocity proportional to the star formation rate squared. And so we can use the differences in the relationship between these two models between the outflow velocity and the star formation rate surface density to tell between these two models in our observations. A lot of work has been done already in this area, particularly with entire galaxy measurements and with stacks of galaxy spectra. So this is a lot of plots to look at all at once, but the main thing you need to note is that all of them are plots of outflow velocity against star formation rate surface density. One of the difficulties in observing outflows is that they are very faint compared to the signal from the galaxy. So in the Chisholm et al. And Rubin et al. Plots, each point represents an entire galaxy. In the Roberts-Bersani et al. And Davies et al. Plots, each point is stacked pixels from a lot of different galaxies. So using entire galaxies or stacked spectra, these studies can increase the signal to noise and resolve the outflows. This is a very useful technique, and some amazing work has been done so far. Outflows have been observed ubiquitously in star-forming galaxies. However, we haven't found much agreement about which model might be a primary driver of outflows. But now with instruments like KCWI, we can start to do these sorts of studies across entire galaxy disks at sub-kiloparsec resolution. And with surveys like DUVET, we can now start to probe scales which feed back most effects. So this is the pilot target, which I've been working on. This is IRSO 8. It's a face-on spiral starbursting galaxy. This is an HST-H alpha image of IRSO 8 with the KCWI spaxel size shown. And so when a face-on galaxy like IRSO 8 emits outflows, the gas in that outflow is traveling straight towards us. Any emission lines from the outflow are therefore blue shifted. The emission from the galaxy itself tends to be quite bright with low velocity dispersion in a spaxel, meaning that it's also quite narrow. The blue shifted emission from the outflow is fainter and broader since there's more turbulence within that outflowing gas. And these two combine to give us an observed asymmetric emission line. So I've been writing a code to decompose these emission lines into their two components, which I've called coffee, since coffee goes well with duvets to keep you warm. And everything in astronomy needs a nicely forced acronym. Coffee uses two Gaussians to decompose the observed emission lines into its two components. So this is an example of one of those fits. This is the 03507 emission line for one of the spaxels from IRSO 8. In light blue, we have the flow component, and in light purple, we have the galaxy component. And now that we have this fit, we can use it to find properties about the outflow, like the outflow velocity. And we do this by looking at the difference between the means of the two Gaussians and then adding twice the velocity dispersion of the broad Gaussian. This gives us the maximum outflow velocity. This is similar to V90 from absorption line studies, so that we should be able to compare that later. So we can apply this code. Thank you. So we can apply this code across the face of IRSO 8. And what we find is that IRSO 8 has evidence for outflows across the entire galaxy disk. And so on the left here, we have a map of the phi UV flux for IRSO 8. And then on the right, at the same scale, we have a map of the outflowing velocities for all of the spaxels in IRSO 8, which have a signal to noise greater than 20 in the continuum. So we find outflows which have velocities ranging from 100 to 500 kilometers per second. Almost 100% of spaxels within the half-light radius have an outflow, and 40% of spaxels within R90. So from local galaxies like M82, what we would expect an outflow to look like is originating from the center of the galaxy and then flowing outwards in a biconical structure, so that if you look down on it, it all looks like it's coming from pretty much the center of the galaxy. But that's not quite what we see when we look at IRSO 8. We have outflows originating from across the entire galaxy disk in IRSO 8. And so we think that this is showing a little bit more of a complex relationship between outflows and the CGM. So as you have, even though you have the main part of the outflow originating from somewhere near the center of the galaxy, as it falls back onto the plane of the galaxy, it will meet outflows which are coming up from underneath and meeting that, smacking into each other and causing a whole lot of turbulence in this area between the galaxy disk and the CGM. So we think that in starbursting disk galaxies like IRSO 8, there may be a much more complex baryon cycle happening. But we don't just want to understand the geometry of the outflow, we also want to go back to this question of whether energy or momentum is primarily driving those star formation outflows. And we want to make this plot of V out against star formation rate surface density. And so here it is, the outflow velocity against the star formation rate surface density. Each point in this plot is from ISO 8, a different spaxel, and the blue line shows the median for bins of star formation rate surface density. The dotted line shows the energy-driven model, and the dashed line shows what we expect for the momentum-driven model. And we can see that ISO 8 is consistent with the energy-driven outflows. So I wanted to test this a little further. And so here I have plotted the mass loading factor against the star formation rate surface density. The mass loading factor is a measure of the efficiency. So it compares the outflowing mass rate against the star formation rate. So if it is greater than 1, you expect to have more mass outflowing from that spaxel than is being converted into stars. Again, all of the blue points come from ISO 8, and the solid blue line is the median of those values. The dotted blue line comes from energy-driven models, which are used in the simulations by Kim et al. 2020. And we can see that again, ISO 8 is consistent with energy-driven outflows. So in summary, the DUVET survey is using observations from KCWI on Keck to test feedback models on sub-kiloparsec scales. We've found evidence for metal poor inflows and metal enriched outflows in an edge-on system. Outflow measurements have been made across a face-on galaxy, and they suggest that there's a complex baryon cycle in starbursting disks. And ISO 8 has a star formation rate surface density to outflow velocity relationship, which is consistent with energy-driven outflow models. These results have recently been submitted, or will be submitted, in 2 papers. And I am currently applying coffee to more galaxies from the DUVET survey. Thank you.
Wow, very good talk. Thank you. And any question from the audience? Yes. Antonia.
Hi, can you hear me?
Yes.
Yes, we can hear you.
Hi, Bron. Thank you for your talk. It was really great. It was really impressive results. And I have a question regarding the very last thing you said, that you're applying coffee to other galaxies in DUVET. Can you tell us a little bit of if you found something right now, or maybe a little spoiler of what's coming up?
Yeah, so at the moment I am actually working on continuum subtracting all of our data, which is somewhat more tricky than you would expect since they are such highly star-forming galaxies. But I have some preliminary results from one of my galaxies, and this hasn't been fixed at all or like checked at all, but it does look like that galaxy is also following the energy-driven outflow model. Yes, but I do need to go back and make sure that all of those fits are fine. So that's very preliminary results.
Sounds great, super great. Thank you so much. Thank you for your talk.
Thanks.
Yeah, there is another question from Kim Wee. The question is, are you including contributions from no energy AGN?
No energy AGN. No, we're not. As far as we're aware, there aren't any AGN in these galaxies. I haven't heard of no energy AGN before, actually. I would assume that they are the AGN that are just dormant. Is that right?
I think maybe, yeah.
But no, we're not
including
like
those. Liner. Like Linus, yes.
But yeah, we have selected these galaxies to not include AGN.
Okay, thank you. Any other question? Yes, Julia.
Great talk. I really, really enjoyed it. I was just wondering, what kind of spatial resolution do you need to observe these outflows, like to make sure that they're coming, that what you see is not just noise, or I don't know, to make sure that you see things, when you say that things are coming from the whole galaxy, they're actually coming from the whole galaxy, and not maybe it's just, you know, the spatial resolution that it's not great.
So this is actually, I think, the highest spatial resolution this has ever been done at. So we've got them on sub-kiloparsec scales, but we have actually binned up our data to see what happens if we decrease that spatial resolution. I have a slide for this. And so here what we have is secularized bin diameter. So this is as we increase the number of spaxels that we are including in a bin. And this is the correlation coefficient between the outflow velocity and the star formation rate surface density. And so if you just look at the blue line, we see that the correlation between these two, the correlation between these two parameters actually increases as we bin the data until we get to about a bin diameter of 500 parsecs. Kiloparsecs. I think that's wrong. Yeah, and so you need at least resolution of 500 parsecs, I think, before you can say anything definitive. But what we do see is that this relationship becomes much more sharp as we go higher in bin diameter. Yeah.
Okay, cool. We have a last question from Ni Song Yong.
Oh, Bron, very nice talk. I'm interested in actually about your results showing that the outflow is mostly driven by energy, not by momentum. So I also heard from a lot of people doing galaxy simulations, some people just prefer the momentum-driven outflow. It's just completely based on the observations. So do you think your observation, if you're adding more galaxies, will give you a sort of the better constraint in terms of, you know, the simulation, okay, which type of outflow is actually dominating, in particular for this star-forming galaxy that you choose?
Yes, definitely. And that is what I'm working on at the moment, adding more galaxies to this. It should definitely better constrain this. But we are focusing on those starbursting systems. And so while this might inform which is dominant in those systems, it may not tell us much about the star, like normal star forming systems, and which is dominant in those conditions. However, this should be useful for simulations, at least for starbursting galaxies.
I think I should be able to, you know, looking forward the more result with more galaxies. I guess it might be the case by case, but anyway, it's very interesting result. Thanks.
Yeah, thank you.
Thanks, our first speaker, Bron.